In this video, we're going to introduce what is known as the orthogonal projection matrix. It provides a convenient means for computing the orthogonal projection of a vector onto a subspace. So let's suppose we have a subspace of Euclidean space Rm with an orthonormal basis consisting of the vectors u1, u2, u3 up to u sub k. So each of these vectors has length 1 and they are pairwise orthogonal, and we're going to assume that k is less than or equal to n. A very typical example would be in R3, where we have two orthonormal vectors that would generate a plane whose span is a plane. And let's suppose we start with a vector b that's also in Rm. It's not necessarily in the span, so we know how to form the orthogonal projection. The orthogonal projection of b onto the subspace W, W being the span of these vectors, we take u1 dotted with b, multiply that by u1, take u2 dotted with b, multiply by u2, and so on and so forth down the line, ending with uk dotted with b times the vector uk. So these are dot products, and then this is ordinary vector multiplication right here. This is a scalar times a vector. Now, if these vectors were just orthogonal but weren't unit vectors, then I would have to divide by the lengths here in order to make unit vectors. So this is a very nice property of orthonormal bases. So we're going to introduce a new matrix Q whose columns are formed using the orthonormal basis vectors u1 up through u sub k. So this is a matrix that has m rows because we're working in m-dimensional space, and it has k columns because there are k of these vectors. Now, let's compute Q transpose times Q. Keep in mind that Q is m by k, so Q transpose would be k by m. A k by m and an m by k is going to give me a k by k matrix. So the transpose of Q would be given by taking these column vectors, taking their transposes, and stacking them up like this. This is a row vector, this is a row vector all the way down, and then here's Q. Now think about how we would compute this product. We would take all possible row columns here and multiply them by all the various column vectors over here. So for example, I would take u1 transpose times u1. I would take u1 transpose times u2, which would give me that entry, and so on and so forth down the line, u1 transpose times uk, right there. And then I would go to the next row, u2 transpose times u1, which is right there, u2 transpose times u2, which is going to go right there, and so on and so forth all the way down the line. And the very last product is going to be uk transpose times uk. Now let's think about each of these quantities. Each of these is actually a dot product. So this is really u1 dotted with itself. This is really u1 dotted with u2, and so on and so forth. uk dotted with u1, and this is uk dotted with uk as well. Now, u1 dotted with itself is going to be 1. That's because the u's form an orthonormal basis. And it's because they're orthonormal, we know that the vectors are pairwise orthogonal. So this dot product is 0. All of these dot products are 0, except the ones along the diagonal. And those dot products are all equal to 1. So we have a bunch of zeros, but then we have ones down the diagonal because this is an orthonormal basis. That means that Q transpose times Q is actually the K by K identity matrix. Now, the orthonormal projection matrix P is defined to be Q times Q transpose, not Q transpose times Q. These two matrices may not be the same. This matrix gives us a convenient tool, convenient means for computing the orthogonal projection. Here's what we do. We take P times B. That's going to be Q times Q transpose B. So here's Q, U1 up through UK. These are each column vectors. And then Q transpose would be the transposes of these vectors written this way. So that's a row vector, that's a row vector, so on and so forth down the line. Here's my vector B. So this is matrix multiplication, all of these, even though B is a vector. Now, how do we expand this over here? Well, we can do the orderings in different ways, but this is going to be U1 transpose B, U2 transpose B, and those are all dot products. So the first entry is U1 dotted with B, U2 dotted with B, all the way down the line. UK transpose multiplied by B is UK dotted with B. And then we have the column vectors U1 up through UK. So this is a scalar, that's a scalar, that's a scalar. What we're going to do is we're going to take this scalar times that vector, add it to this scalar times that vector, and so on and so forth. And this is what we get. But this is merely the orthogonal projection of B onto W, which we saw on the previous page. So here is the upshot. Once we form our projection matrix Q times Q transpose, and that's formed using our orthonormal basis for W, we can calculate the orthogonal projection of any vector B onto that subspace by taking that projection matrix and multiplying it by B. Let's take a look at a simple example. So we're looking in three-dimensional space. I'm going to look at two vectors U1, 1 over root 2, 1 over root 2, 0, 1 over root 2 minus 1 over root 2, and 0. Now these vectors are clearly orthogonal. They are also unit vectors. So they form an orthonormal basis for a plane. A plane because we can see the 0, the third components are equal to 0. So our subspace is going to be the span of these two vectors, which can be visualized as the x1, x2 plane in three-dimensional space. And again, that's because the third component is 0. Here's our vector B. It's 4, 3, 1. It does not live in the span of U1 and U2 because it has a third component not equal to 0. We're going to find the orthogonal projection of B onto this plane using our projection matrix. So we form our matrix Q using these vectors as columns. It is a 3 by 2 matrix. The transpose of this would be 1 over root 2, 1 over root 2, 0, 1 over root 2 minus 1 over root 2, 0. So Q is 3 by 2. Q transpose is 2 by 3. It's fairly easy to check that if I take Q transpose times Q, I get the 2 by 2 identity matrix. Now the projection matrix is Q times Q transpose. I won't show it here, but if you multiply Q times Q transpose, you would have a 3 by 2, a 2 by 3, so you get a 3 by 3 matrix, and its entries are 1, 0, 0, 1, 0, 0, 0, 0, 0. We can use this matrix to calculate the projection, the orthogonal projection of P onto W, of B onto W. Here's my matrix P, my projection matrix. There's my vector B, and when I compute this product, I get 4, 3, 0. Now this intuitively makes sense because the vectors U1 and U2, they had a Z component of a third component of 0. So they're living in the plane, the horizontal plane. So if I project this vector onto the horizontal plane, its third component should be 0. So that's what we see. Now we could have also, under the old method, calculated this orthogonal projection by taking U1 dotted with B, multiply that by U1, take U2 dotted with B, multiply by U2. Let's consider U1 dotted with B. We'd have 1 over root 2 times 4, so that's 4 over root 2. 1 over root 2 times 3, that's another 3 over root 2, plus 0. So that would give me 7 over root 2. I would multiply that by my unit vector U1. The dot product of U2 with B is 1 over root 2. That's fairly easy to show. and I would multiply that by U2. So I have 7 over root 2 times this vector, plus 1 over root 2 times that vector. If I compute this, I get 430, which is exactly what I got when I used my orthogonal projection matrix. So the upshot is that we can construct a projection matrix and we can realize or compute our orthogonal projection simply by performing matrix multiplication. Here's a problem for you to work on. Here are 3 vectors in 4-dimensional space. U1 is a half minus 1/2, 1/2 minus a half. U2 is 1 over root 2, 0, 0 minus 1 over root 2. This is a root 2. And U3 is 0, 1 over root 2, 1 over root 2, 0. These vectors are clearly unit vectors. It's fairly easy to show that that's a unit vector, and they are orthogonal. Let me just check that. This would be positive, negative. Okay, so these two are orthogonal. These two are clearly orthogonal, and actually the others are orthogonal. So I do believe these are orthogonal. They're clearly unit vectors. So W is going to be the span of those 3 vectors. Find the orthogonal projection matrix P and use it to compute the projection of this vector B, 1, 2, 4, negative 3, onto W, which is the span of this.